Welcome to Calculus Concept 1-4 video lesson on functions review. Three short little boxes here to talk about, and all of this stuff should make some sense to you because we've seen most of this stuff before. So I'm going to go through it pretty quick. Here's the first vertical line test that we're going to talk about here. Of course, the vertical line test says the following thing. It says if a graph passes the vertical line test, then that graph represents a function. So that's the first part of that we need to remember for the vertical line test. If a graph passes the vertical line test, which I'm calling the VLT, by the way, then that graph represents a function. So two little quick basic questions right down below. No one's trying to trick you here. For this one here, which graph represents a function? You're going to pick A, B, C, or D. And then secondly, over here, which graph or which diagram does not represent a function? And you're going to pick A, B, C, or D. So there you go with that one. Okay, box number 2 here is all about domain, range, and interval notation. So we need to get very, very good at looking at a graph and picking out the domain and the range from that graph. So take a look at here at this circle I have, okay? The domain values, of course, are all of the x values that the graph takes up. So what you want to do is look along the x-axis and remember that this is the x-axis, and the lowest x value that I have is over here at -1, and the biggest x value I have is over here at 5. So if I was to just highlight the part of the graph that the x's are on, it goes from -1 to 5. So the domain written in interval notation would be a bracket, -1, 5, and then another bracket. The reason we're using the brackets is because the -1 and the 5 are part of the domain. For the range, we do the opposite. We look at the y values. So here's the y-axis, this one right here, and I look at the y values, and they go from there and they stretch down to there. So if I map it back to the y values or the y-axis, the lowest y value looks like -3 and the highest y value looks like 3. So the range would be from -3 to +3, starting from the lowest and going to the highest. Similarly, for the domain, we go from the lowest over to the highest. So we need to be very, very good at looking at graphs and coming up with the domains. Here's another little example here. Let's find the domain and the range again using interval notation. Well, the x-axis is here, and I can see that every single point on this particular graph can be mapped back to the x-axis. So therefore, the domain for this guy is going to be all real numbers. Okay. The range is a little bit different though. Okay. The lowest range, the lowest y value I have is here, and then they go up from there, right? This maps back to the y-axis. So therefore, the range written in interval notation will be the lowest one that I can find is 1, and then the highest one that I find is positive infinity, and I use a parenthesis. It's very important to note to put a parenthesis here because you never ever put a bracket on an infinity sign. Okay, let's try the third one here. We want to find the domain and the range. Notice that this little guy over here is a circle with an open dot. That means that that point is not a member of the domain. So when I'm looking at the domain values, I'm going to map back to the x-axis. I go from here, and then it looks like this graph goes on forever. So the domain would be, the lowest x value would be -1, but I would use a parenthesis here because of that open circle. I do not include it. So it'd be -1 to positive infinity. And then the range, of course, is the y values. So if I map back to the y-axis, the lowest y value I have is a -3, and this looks like a line. So this looks like the only interval where the y's are going to be. That's my range. So the lowest one would be a -3. So again, -3 all the way up to 1, and this one would be a bracket because 1 is a member of the range, because that's included, because I can see it definitely. But -3 is not because of that open circle. So we need to be good at looking at those open circles as well. Okay. Here is a U-try. So I want you to come up with the domain and the range for this particular function and write it in interval notation. Okay, hopefully you got the right answers. Here's how I got it. For the domain value, I take the points and I map them back to the x-axis. So I'm going from there to there, and I'm looking at that interval. That is from -1 all the way to 6, which is how I got these points, -1 and 6. I'm not going to include the -1 because of the open circle, but I am going to include the 6. Therefore, I would have parenthesis -1 comma 6 bracket. For the range, I'm going to map these points back to the y-axis. So map this point there and map that point there. So this right here represents my range. The lowest is 1, the highest is 5. That's how I got the points 1 and 5. I include the 1 because clearly that point is colored in, but the 5 again is not colored in, so I do not include that one. Therefore, I get bracket 5 comma, or sorry, bracket 1 comma 5 parenthesis. So hopefully you guys got the right answer on that, and we will practice more when I see you. Okay, sorry, I know I said 3 boxes, but it's 4 boxes. My bad. All right, here we go, last one. Let's talk about the domains of functions. There are 3 big types of functions so far that we have studied in our mathematical career. Okay, they are polynomial functions, rational functions, and radical functions. So let's start with the easy and then work our way over to the more challenging. Polynomial functions, they look like this. X to the third minus 2x squared plus 5, or a negative 5x to the 11th, plus a 2x to the 9th, plus a 9x. They're very nice looking, and the really important part is that the domain of all polynomial functions is always going to be all real numbers. This is the beauty. We love polynomials. Thank you, polynomials. We love you. Let's move over to rational functions. Remember, a rational function is nothing more than a polynomial divided by another polynomial, like 1 over x plus 2, or x plus 5 over x squared minus 4. And we used to call these things back in pre-calc, p of x over q of x, you may recall. P of x again over a q of x. And the way that we find the domains for a rational function is we always set the denominator equal to 0 and we would solve. So as an example, if I wanted the domain for this guy, I would set x plus 2 equal to 0 and solve, and I would get x is equal to -2. So therefore, one way to represent it in set notation, you may recall, is all real x, such that x is not equal to -2. This guy, same thing, set the denominator equal to 0 and solve. That's how you find domains for rational functions. Radical functions are a little bit more interesting. There's 2 different kinds. Notice there's a red star here. There's 2 different kinds. If my index is even, like it is in this case, and remember the index is the number just sitting outside of the radical, then all I have to do is set my radicand greater than or equal to 0 to find the domain. So 5x plus 9 is greater than or equal to 0. So 5x is greater than or equal to -9. So x is greater than or equal to -9/5. Wonderful. That's only if I have an even index. If I have an odd index like this one, you may recall that the graphs of these are smooth and continuous. So therefore, anytime I have an odd index, the domain is always guaranteed to be all real numbers. How nice is that? Thank you very much. So the tricky parts are just knowing when to set something greater than or equal to 0 for radical functions and when to set something not equal to 0 for rational functions. Okay, that's it. We'll practice more in class.